All right, this is the video for 1B3 homework. So I'm going to write that in up here so that we have that on the list. And we're going to be looking at proportions and something called CPI. So inflation, which I'm sure many of you have heard about, and especially in recent years, is the rise in the general level of prices of goods and services in an economy over time. CPI is the Consumer Price Index. So this is a value or a monthly number that reflects the changes in prices paid by urban consumers for a representative basket of goods and services, which we use to track inflation. So, I don't know, I think you can look up what the basket of goods and services are somewhere, but, imagine going to the grocery store and you buy these 20 items, okay? And they track those 20 same items every month and see how the change in price has been. So CPI charts usually are going to be provided in the question, and you'll have all the information you need. You don't have to look up anything on those in Newton. The key to the success on these problems is going to be to set up your template with your labels and then fill in your values and cross multiply. So for example, this is the CPI, this member, the price of the goods and services in that basket, say those, 20 to 25 items. I don't remember exactly how many items it is, but you go to check those out. And in 2017, they were $245.12. Back in 1977, those same goods were only $60.60. So you can see kind of the comparison over the years. We never use the actual year in part of our cross multiplication. We use it as a label. So let's look at an example. It says, my first car out of college cost $9,800 in 1987. What would that be in 2017 if it kept up with inflation? In other words, it follows the CPI model. So their setup is you're going to have 2 years that are involved in your question, and then you're going to have your actual value over your CPI for that year. So we already know both things in 1987. If we look up here, we can get our CPI. We know our actual value. So 9,800 over the CPI, which was those prices of goods and services, which was 113.6. You can drop off the zeros if it's just zeros. And then we don't know what that car would have cost in 2017, but we do have the CPI for 2017. That's 245, and I'm going to put the 0.12, and again, just drop off that last zero since it doesn't change the value. Then we're going to take our calculator and cross multiply this. So 9,800 times 245.12. That is 2402. Sorry, my calculator flips off every time I do that. 176 equal to, the other multiplication would be 113.6x. Divide that by 113.6. And they didn't give us rounding rules, so I'm gonna do whole number for the round. They should in Newton give you the rounding rules. So this would be 21,145.9. So that 0.9 is going to bump that up to a 6. So $21,146. So that same car, make and model similar enough, that cost me $9,800 in 1987. If inflation is how the price has changed, that would then cost 21,146. Now, what we actually find is sometimes things in different markets do not follow inflation exactly. Sometimes they're under or they're over. But this is what we would expect if it followed inflation. So let's do a couple more. It says if a hamburger cost 38 cents in 1979, what would be the equivalent price for the year 2017? So our 2 years in question are 1979. Remember, these are just labels. In 2017. The actual value, I'm going to make this in cents. So that's going to be 0.38 for the actual cost in 1979. CPI for 1979 was $72.60, so 0.6. I don't know what the burger cost if it keeps up with inflation in 2017, but I do know the CPI for 2017. Those same goods and services that used to cost $72.60 now cost $245.12. So if we cross multiply, this would be 0.38 times 245.12. I'm going to write that. That's 93.1456 equal to 72.6x. If we do our other diagonal, we're going to divide by that 72.6. And that gives me, we're going to round this to the nearest cent since we were in cents before, $1.28. So $1.28. So that's what that hamburger that used to cost 38 cents should cost according to inflation. If the, sorry for my runny nose, struggling through that. If the price of an oil change is $45 in the year 2015, okay, that's going to be our year of starting. What was the equivalent price back in 1985? And it doesn't matter which column you make which year, just make sure you keep things together. So $45 is my actual value. Forgot to write CPI down here. And then I need the CPI for that year. So 2015 was $237 exactly. And in 1985, we don't know the price of the oil change, but we know the CPI was 107.6. So we do 45 times 107.6. That's 4,842 times equals 237 times x. We need to divide by the 237 to get x by itself. And we're going to, since they didn't give rounding rules on some of these, I'm going to go with the general rounding of what the original problem was. So it was rounded to the whole number. Like I said, Newton usually is very specific. So that would just be $20. Price of tuition in the year 2010. Okay, so actual value, CPI. If the price in 1995 was $18.65, we know the CPI for both years because they're in our chart. CPI for 1995 is 152.4. CPI for 2010 is 218.1. So we're looking for tuition price in the 2010. So that's going to be 218.1 times 1865. So 406,756. 406,756.5 equals 152.4 times x. We're going to divide by the 152.4 since that's next to our x. And again, I'm going to round to the nearest whole since the original problem was set up that way. So that's 2,669.0. So the 0 doesn't change that 9. So 2,669 would be the tuition cost. And then find an equivalent price of a calculator in 1985 if you paid $15.89 in 2020. Okay, so we have 2 years, 1985, 2020. Actual values and CPIs. The actual value of the calculator was $15.89 in 2020, which had a CPI of 258.8. 1985, we don't know the price of the calculator then, but we know the CPI was 107.6. Cross multiplication, we get 258.8x equals 107.6 times 15.89. That is 1709.764. So 1709.764. And then we divide that by the 258.8. And we're going to go to 2 decimal places. Again, I'm just following the rules of the setup since there were no direct directions on this one. So that's 6.606. That's 6 after that 0. We'll bump it up to a 1. So that calculator would have cost $6.61. Okay, so let us look at the continued part. This is just some more questions from this section. So the price of a McDonald's Big Mac was 65 cents in 1973. What would the price of a Big Mac be if in 2019 if the inflation were the only factor impacting the price. That means we don't know if they had other outside factors. We're assuming we just followed inflation. So we're assuming we followed CPI. Round our answer to the nearest cent. Okay. So I'm going to write my two pieces of information I need, which is 1973 and 2019. We'll need actual value and CPI for each of those. We don't know the 2019 price. We know the price in 1973 was 65 cents. CPI in 1973 was 44.4. CPI in 2019 was 255.657. So if we cross multiply, we'll be getting 0.65 times 255, oops, 25, 0.657. And that is 166.17705 equal to 44.4x. Divide by 44.4. And I'm going to round to the nearest cent like they have here, because it also actually tells me on this one. That'd be 3.74. So $3.74 now for that Big Mac, if the only thing that happened was we followed inflation. Now this question is asking you if something actually did follow inflation or not. It says, if the average price of a house grew with inflation, then the average price of a house in 1992 should have been $97,337. However, the actual average price for a house in 1992 was $144,500. Did the average price of the house grow faster or slower than the inflation? Well, if this is the expected based on the CPI, and this is what we actually see. So we are higher than the inflation rate. So this one is growing. The average price of a house grew faster than inflation. So that throws out C and D because both of those say slower. And then how would we know that? Well, it says the average price of a house grew faster than inflation because the actual is higher than the expected. That would be the truth. This doesn't make sense because it says the actual would be lower than the expected. That means we grew slower. So A would be the correct answer there. Number 8 says the minimum wage in 1985 was $3.35, and it was $5.15 in 2005. So those are both actual values. It said if minimum wage had grown within inflation, what would have been the expected value in 2005? So even though we know this is 515, we want to know what we should have expected based on CPI. So this is one where we have been given too much information, essentially. We only need to use the $3.35, and we're going to compare, put that over at CPI, what the expected outcome should have been if inflation was followed. So 195.3, we're going to solve that. So 3.35 times 195.3 is 654.255 equals 107.6x. Doing our cross multiplication, so we're going to divide by the 107.6 to get that away from the x. And that would have been 6.08 if we round to the nearest cent, which is what they want us to do. So this is what should have been expected. And the actual wage that people made in minimum wage in 2005, the average was $5.15. So it's very interesting. This is a lot of times why people get into discussions about, wages not being enough, is because prices of housing and goods a lot of times are growing faster than the rate of inflation, but our wage system is growing slower, because we're almost a full dollar under what we expected by the inflation rate. So if you're not making enough, it's making everything else seem more and more expensive. So that's why those arguments are always really valid and really interesting. And you can kind of show it with the math. So we have another part to section 1B.3. It's part 2. It's having just some more practice with proportions and using comparisons. sorry. So we're going to look through this. This is going to talk about just looking at comparing different ratios to each other. So we're going to set up our templates and use our A over B equals C over D and cross multiply, make initials to make sure we line up the proportions, use our good reading comprehension, cross multiply, and solve for the unknown. Follow our directions on rounding, and we will also look at what if questions, finding out what a value would be if there were proportional to another set of data. So again, kind of like, what if this matched this? Even if we know the actual value, what would they have been like if they were proportional to a reference value? So let's look at this very first one. It says in 2021, Madison Square Garden employed 8,900 people. For a basketball game at the Garden, there are seats for 19,812 fans. And then this is just saying, what is the number of fans per employee? So this one's not really a proportion to solve. A lot of these are just, hey, do you remember what a rate is? Then we're going to jump in and do some comparison ones. So we just want to know the fans per employees. We want to know what that is. So there are, and notice fans is first, so that's going to go on top, then per. So 19,812 fans divided by the employees, which was 8,900 employees. So let's divide that. 19,812 divided by 8,900. That's going to be round to the nearest 10th. So it's about 2.2 fans per employee at that basketball game. All right, let's look at another one. There are 58 Disney feature films, and there are 285,713 residents of Orlando. How many people live in Orlando per feature film? So again, we're not comparing it to any other situation. We're just trying to figure out that ratio or that rate. So let's look at that. That is people first. So that's going to be the residents going on top. So 285,713 people divided by the feature films, which was 58 feature films. And we're supposed to round to the nearest whole number on this one. So 285,713 divided by 58. That's 4926.0. So that 0 does not bump that 6 up. So 4,926 people in Orlando that live in Orlando per feature film. That's just giving that context to that number. Now this one, notice there is, there's a third piece of information thrown in. So this is where we're going to start seeing, when you see more than just two pieces of information, we're usually going to be doing some kind of proportion when we're doing these comparisons. It says Texas averages 198,106 deaths each year to a population of 29,472,295. How many deaths could we compare to just 100,000 people in Texas? So we're looking at a ratio of death over population, where we were given 198,106 deaths with this total population. And we want to scale this to, well, how many deaths is that per 100,000 people in Texas? So population to population, we're scaling this down, essentially. We're trying to see, this is total population in Texas, but what if we just wanted to know how many deaths do they expect per 100,000 people? So we're going to cross multiply. So that's 198,106 times 100,000. And that's going to be really big. I'm not going to write all this down. Then we divide by the 29,472,295. Because remember, you would divide by the one that's next to the X when we cross multiplied. So that's going to be round to the nearest whole number, 672. So we have approximately 672 deaths per 100,000 Texans. Okay. Indiana averages 82,650 births each year to a population of 6,745,360. So we're going to be looking at, again, scaling this down to what 100,000 people, how many births would we expect? So we're going to do birth to population, and we have our actual values they gave us, number of births for the total population, equal to how many births would that be for just 100,000 people in Indiana? So 82650 times 100,000, and then divide that by 6745360. And we're rounding to the nearest whole. If you notice, I have a 0.2, so it's not going to bump it up. So it's approximately 1,225 births per 100,000 people in Indiana, or Hoosiers, if you want to say. Okay. All right, and then the city of Tourist has 298 hotels with a population of 386,202. In Tourist, how many people, not counting visitors, just their population, do they have per hotel? Notice there's no comparison to another, we're not scaling it to any other value. We just want that ratio, that rate again. So round to the nearest whole, but be careful on this one. It's people per hotel. So 386,202 people per 298 hotels. So 386,202 divided by 298. That is going to be round to the nearest whole. That'd be 1295.9. So that 0.9 is going to bump that up to a 6. So 1296 people per hotel. So if everybody in their country had to go live in a hotel for the evening, they would roughly have about 1,296 people. So 1,296 people per hotel. All right, so we're going to flip over to the next page. Okay, so we're going to be using proportions to do some comparisons. So for this problem, it says Iowa has on average 37,785 annual births compared to 30,530 annual deaths. If Maine was proportional to Iowa in annual births to deaths, and Maine averages 14,676 annual deaths, how many annual births should Maine expect? So we're missing this part for the question. So we have Iowa births is 37,785. Iowa deaths is 30,530. And Maine deaths are 14,676. So we're going to cross multiply. So some of these I won't write out all of my work just because to save time. But you should practice doing, at least one step of writing your work where you do the cross multiplication step. And then that's the one we know. And then this is 30,530x. We're going to divide by the 30,530. And we're rounding to the nearest whole. So they should expect, if Maine is still proportional to Iowa in terms of this ratio, they should expect 18,164 because the 0.5 would bump that up to the nearest whole. So that would be births in Maine. Okay, let's look at another one. Alaska has 49 Starbucks and a population of 741,204, while Delaware has 25 Starbucks. If Alaska is proportional to Delaware in Starbucks to population, how many people would Delaware have? So we're looking for the population of Delaware. So Starbucks over population for Alaska. Equals Starbucks over unknown population for Delaware. Cross multiply, so we'll do the 741,204 times the 25. since that we know both parts of that diagonal. And then we're going to be dividing by the 49 since that's across from the x. So that's going to be to the nearest whole, that'd be 378,165. So 378,165 people in Delaware. Okay. San Francisco has 220 parks with a population of 833,000. San Diego has 340 parks. If San Francisco was proportional to San Diego in parks to population, how many people would San Diego have? Round to the nearest whole. Okay, so parks over people for San Francisco. And we're looking for the number of people in San Diego. So we know they have 340 parks, but we don't know the number of people. So this time, again, I know the 340 times 883,000. I know both of those numbers, so we'll cross multiply that first. And then we're dividing by the one that's always across from the x. So divide by the 220. Round to the nearest whole. This is going to be 1,364,636. 0.3 will not bump that up, so it's just going to be 636. So their population would be 1,364,636 if the ratio of parks to population is the same in San Diego as it is in San Francisco. So this is San Diego population. All right, and it is estimated. So this last portion of section 1B.3 has to do with what if we're throwing in the words millions, billions, and trillions? Should we convert things to scientific notation? What should we do in those scenarios? Or should we write out the full word? If they say 5 million, should you write 5 and then move the decimal over so that you have all the zeros? So there's a couple different scenarios that we could come up with. And this one, I found a typo on it. So let me fix this. This was still supposed to say 250,000 on that. So just so we can look at that. So this is our first example here. Notice that it says state A averages 250,000 deaths per year with a population of 22 million. So notice my first fraction sets up the 250,000 or 205,000, sorry, divided by 22 million. And then state B averages to 12,003 deaths per year with a population of 0.99 million. So see, they've given us all 4 pieces of information, but that's not what they're asking us to find. They're saying if state B was proportional to state A, so right now we're assuming they're not, then how many deaths would state B expect to have? So notice that's why instead of putting the 12,003 on top, I'm putting the X, because we're saying, okay, well, state A and state B are different because if you actually divided both of those ratios, they're not the same. We're asking what if they were the same. So if this state is the same proportion to deaths to population as this state, what should we expect state B to have for number of deaths? So when you go to look at this, I'll write it better because sometimes when you write it in Word, it doesn't stack nicely. What you're going to see is they're both out of millions on the bottom. So when we go to cross multiply, instead of actually working this out, I'm going to just write it out in multiplication like I did above. Equals 22 mil x. We divide by 22 mil to get it to go away. This is why I didn't convert anything yet, because both of these measurements were in millions. So the million part, the word million, is the same. So we can cancel that out. So we're just doing 205,000 times 0.99 and then dividing that by the 22. So they should have 9,225 deaths in state B if it was proportional to state A. So what we're finding is that actually state B has a higher death per population rate than state A did. It looks like a lot more deaths, but there's a lot more population in state A. So we would expect, 3,000 less people to die in state B if they had the same ratio as state A. All right, let's look at another one. So a lot of these, they give you all the information, so you have to really read what is the question asking us to find. What proportion, what if, are we finding? So 27 Starbucks in Atlanta with a population of 0.5 million. Brooklyn has 142 Starbucks with a population of 2.53 million. If Atlanta was proportional to Brooklyn and Starbucks to proportions, how many Starbucks should Atlanta have? So we're saying we don't know how many Starbucks Atlanta has. Everything else is given in the problem. So we're ignoring this 27 because we're saying this is what we actually know about Atlanta. What should Atlanta be if it matches Brooklyn? So Brooklyn had 142 Starbucks and 2.53 mil for the population. Atlanta had 0.5 mil for the population. So I'm going to write this out again. So it's 2.53 mil times X equals 142 times 0.5 mil. We're going to work out, actually go ahead and do the division. 2.53 mil is next to X, so we'll move that over. And because they both are in millions, we can cancel out the word million. So we're just working with the numbers. So that's 142 times 0.5 divided by 2.53, and we're rounding to the nearest whole. So this is approximately 28. So for Atlanta to match Brooklyn, we need another Starbucks, right? They need one more Starbucks for them to be proportional to Brooklyn. For the next one, it says there are 27 Starbucks in Atlanta with a population of 0.5. Again, Brooklyn has 142 with a population of 2.53 million. If Brooklyn was proportional to Atlanta this time, how many Starbucks should Brooklyn have? So this time we're saying, okay, well, what if instead of Atlanta matching Brooklyn, what if Brooklyn matched Atlanta? So we're going to have 27 over 0.5 mil equals X over 2.53 mil. We're going to cross multiply. So 27 times 2.53 mil equals 0.5 mil times X. Divide both sides by the 0.5 million. And again, the reason I'm not writing like our scientific notation is because I know they're both in millions. So we're going to get that cancellation of units. So this is just 27 times 2.53 divided by 0.5. And if I round to the nearest whole again, that'll be 137 Starbucks in Brooklyn. So they would actually need less, right, to be proportionate to what Atlanta had, because Atlanta needed more to be proportionate to Brooklyn. And then one more of these where they have matching kind of millions. Chicago has 570 parks for a population of 2.706 million people. So 570 parks over 2.706 mil. Phoenix has 1.66 mil people, so we don't know how many parks. If Phoenix was proportional to Chicago in people to parks, how many parks would we expect in Phoenix? And they did people to parks. I did parks to people. It doesn't matter on proportions if you stay consistent on the same side. So if you do parks to people, you need to also do parks to people. But if you do people to parks, you need to do people to parks. That's what needs to be consistent. So let's look at, this would be 571.66 mil equals 2.706 mil times X. Divide both sides by 2.706 mil. Notice the millions can cancel on the left side. So that is 570 times 1.66 divided by 2.706. So rounded to the nearest whole number, that's going to be 350. So they would need about 350 parks in Phoenix for that to be proportional. Okay, so what if I encounter one where one of them's in millions, but the other one's in billions? They don't match. Then we cannot easily do this cancellation step. We're going to use, I use scientific notation. Some people like to write out all the zeros and type that into their calculator. That's a lot of typing digits. So I prefer to use scientific notation. So this is just reminding you about scientific notation. We covered that in class already. So I'm going to go ahead and just jump down to an example here. I think this was supposed to, yeah, maybe there was it was supposed to all be on the same page, but it didn't get that way. So we'll just do this. So just to practice before we do any word problems, we're going to try and cross multiply with some scientific notation. I don't like that sometimes they call these X's because that looks like the scientific notation X. So anytime I'm doing scientific notation or I see one in Newton that has like X as the variable, and I see I'm going to use scientific notation, I change the variable to N just so it doesn't get confusing with my times symbol for scientific notation. So for this, what we're going to do is just write out what this looks like. So this would be 2.6 times 10 to the fourth times n equals 5 times 7.2 times 10 to the seventh. For the right side, you can just times the 5 and the 7.2 together. Those are both regular numbers. They're not base 10 to a power. So that's going to be 36. So 2.6 times 10 to the fourth n, supposed to be a 4, equals 36 times 10 to the seventh. So I just went ahead and worked out the numbers out front. And then we divide. So 2.6 times 10 to the fourth divided by 2.6 times 10 to the fourth. So remember, when we divide two scientific notation numbers, you divide the numbers in front. So 36 divided by 2.6. And I'm going to write this out to maybe 5 or 6 decimal places. So 13 point, so we don't ever know if they have a rounding rule later. What are we going to round to? 8461538. And then I know that keeps going, but so this is an approximation. And then it's, remember, subtract the power. So times 10 to the third equals n. Now, if they asked me to write this as a standard number, we would then approximate that by saying, okay, 10 to the third means move this 3 places to the right. So it'd be about 13,846 to the nearest whole number. Another way of doing these is to directly type all this into your calculator. Now, I will caution you when you do scientific notation on your calculator, you want to put the part you divide by in a parentheses. So we're going to be dividing by this since it's across from the n. Otherwise, your calculator may not do the correct steps correct. So if I wanted to do this directly on my calculator, I would do 5 times 7.2 times 10, exponent button 7, and I can go ahead and hit enter for that. So that would be that multiplication on completely worked out and like times the 10 to the seventh part, divided by parentheses 2.6 times 10 to the fourth. That parentheses is so that it divides by both the 2.6 and the 10 to the fourth. And then we have to close our parentheses. That tells us 2.6 times 10 to the fourth is 26,000. And notice that if I was rounding to the nearest whole, yeah, it is the 13,846. So let's try this one. So let's do this one directly on the calculator. See how that works. So 5.91 times 10 to the 6. Notice I'm starting with that one because I know the number across from it, times 6.23 times 10 to the seventh, and then hit enter. That's all that one diagonal, divided by parentheses 4.63 times 10 to the fourth, close parentheses, hit enter. So if I was rounding to the nearest whole on this one, it's going to be a little bit bigger. It's 7,952,332,613. Yeah, because the decimal point's right here and the 3 will not bump that up. So 7,952,332, and then 613. If we rounded to the nearest whole, so that would be ones, thousands, millions, billions. So 7.95 billion. This is pretty big. Okay, so let's talk about some word problems that there's only 2 of these that have different units, and that will be the end of section 1B3. It is a long section, sorry about that. But a lot of this is just rehashing the same types of problems. We're just looking at variations. So Chicago is home to 2.706 million people, and the city sees about 55 million visitors each year. China, a different place, has a population of 1.393 billion. So notice we're not going to get units canceling when we set up the cross multiplication here. If their visitors were proportional to Chicago, how many visitors could China expect? Okay, so I'm going to write these as scientific notation. So 2.706 times 10 to the 6th for the million over 55 times 10 to the 6th. That's our visitors. So this is population over visitors, and this is Chicago. And then we're going to have China, which we know the population, so population goes on top, 1.393 times 10 to the 9th for billion over unknown number of visitors. Now our final answer should be in scientific notation rounded to 2 decimal places. So in this specific scenario, I'm actually going to use the multiplication rules instead of using my calculator, because that'll keep me in scientific notation the whole time. So what I'm going to do is write 55 times 10 to the 6th times 1.393 times 10 to the 9th. Now I could do this on my calculator. I'll just have to change the answer back to scientific notation after I'm done. Times 10 to the 6th times n. So remember, when we multiply two scientific numbers, we multiply the numbers out front together. So 55 times 1.393, that's 76.615. And then we add the exponents, remember, when we're multiplying the numbers together. So that's going to be times 10 to the 15th. Kind of using our rules we learned about scientific notation. We're going to divide by the 2.706 times 10 to the 6th. And remember, when we divide the numbers and then we subtract these powers. So 76.615 divided by 2.706. And it goes out for a while. I'm going to write it at least to 5 or 6 decimal places because I don't know if I need to make any adjustments before rounding to my proper scientific notation form. Obviously, it's not proper yet if it's a 28. So 0.31308. Just writing out a few. And then this would be times 15 minus 6 is 10 to the 9th. Okay, so we want 2 decimal places in our scientific notation. So we have to first get this in proper scientific notation. So remember our little saying Lars, move it to the left, we add 1 to the power. So this is going to be 2 point something times 10 to the 10th, because we moved 1 to the left, so we add 1 to the power. And then it's going to be 2 decimal places. So it's going to be 8.3 because the 1 will not bump the 3 up. So that would be the number of visitors in China they expect in scientific notation. All right, and then the last one for this section, Oz is home to 1.7 million people and the city has 490 parks. Again, China has a population of 1.39 billion, so not matching in units. If the number of parks in China is proportional to number in Oz, that should say. I guess we didn't change the wording. How many parks would you expect in China? Okay, so again, scientific notation to 2 decimal places. Make sure you read your directions. So 1.7 million, which I'm going to write as times 10 to the 6th, since these are different units, over the 490 parks. People in China is 1.393 times 10 to the 9th. Just make sure you keep population in the same row together, and we don't know how many parks. So on this one, we're going to be multiplying the 490 times the 1.393. So there's no adding of the exponents on this multiplication because the 490 is not in scientific notation, but we do multiply the regular numbers together. So that's going to be 68257 times the 10 to the 9th that was still in that diagonal. and I want to make that an N. See, this is where I get into trouble. It's better to make it an N if you're using scientific notation because everything starts looking like a times symbol. And then this is 1.7 times 10 to the 6 times N. We're going to be dividing. So 682.57 divided by 1.7. I'm going to write this out to a few places. 401.51176 times 10 to the 9 minus 6 would be 3. But we want to write this in scientific notation rounded to 2 decimal places. So proper scientific notation would require that we move this 2 places to the left, which means we're going to add 2 to that power. So 4.0 and then round to the nearest 2 places after my scientific. So the 1's going to get bumped up by the 5 times 10 to the 5th. And that would be the number of parks. Now, obviously in the real world, you would want to actually tell people what that is. That's what, move that 5 places to the right. That's going to be 402,000 parks in China if it was proportionate to Oz. So yeah, this is just making sure we practice with scientific notation. So that is it for 1B3. I'm going to go ahead and post this one. I'll have a running announcement that just as I add more videos to it, you'll see those. And then I'll be working on the 2A videos.